Okay, we'll wait a little while. Not very many people have shown up. Can you hear me?
Yes.
Very good.
Yeah.
Then we can get started then. So today we are going to advance to a very interesting part of the course, which is on radiation, essentially. We are going to study how electromagnetic fields radiate, or how electromagnetic current sources and charges can radiate. Okay, and we use the scalar and the vector potentials approach. And then we first start out with studying the case for statics, which you have done before. And then we convert what our old knowledge, the new knowledge, which is for electrodynamics. And then we see how the scalar and vector potentials can be used. And then we address the question as to when static electromagnetic theory is valid. We started out the course by studying static electromagnetic theory, and when can we use those theory? And then something that is in between static and dynamic is called quasi-static electromagnetic theory, and we study when that is valid as well. Okay, so when the source radiates, it becomes very interesting. So we can look at the left-hand figure. This figure is the electric field of an electric dipole very close to the source. Okay, and in this field, it's not time varying. However, when the field is time varying, if this dipole is time oscillating back and forth, it will give rise to a field pattern that looks like this, where I have only shown the upper half space. And you can actually look at this and you can see that there's a dipole in the middle and it's oscillating back and forth. And you can see that because it is oscillating back and forth, it sends out waves away from the source point. The reason why it sends out waves is because the electromagnetic field cannot keep up with the changing sign of the source, and the electromagnetic fields have to break away. And when they break away, they form lump of energy that propagates into outer space. And we use that for wireless communications, and we use that for sensing, remote sensing, and radar, and that kind of technology relies a lot on radiation. Okay, so let's look at the static theory first and revisit that. For static theory, we have done that before. We say that if we have static fields, then Maxwell's equations are essentially just curl of E equal to 0. And then we have curl of H equals to J. The first one is Faraday's law. The second one is Ampere's law. And we have assumed that partial T equal to 0. So we can throw out terms that are unimportant. As the revisiting of the previous knowledge that we have learned, in order to satisfy equation 1, we let E be equal to the gradient of a scalar potential. Okay, and using the fact that gradient of a curl of a gradient is always equal to 0. Okay, this is always true. And then the first equation is always satisfied. Okay, by just assuming a very simple thing like this, the first equation is satisfied. And then you can also look at the third equation of Maxwell in the static regime, which is divergence of D equal to 0, equal to charge. And this can be written as divergence of epsilon E equal to charge. And now with E equal to gradient of phi, then the Gauss law or Coulomb's law, whichever you want to call it, becomes this equation. You just substitute this into this one, you get this equation. And let's assume that epsilon is a constant. And if epsilon is a constant, then this equation can also be written as epsilon, the divergence of the gradient of phi equal to rho. And this will furthermore become let me see. It doesn't like this. Okay, and this would just become Laplacian of phi equal to rho over epsilon, which is Poisson's equation. Okay, that's just Poisson's equation. And then how do we solve the magnetic field part? The magnetic field part, what we do then is that with the anticipation that divergence of B is equal to 0, which means the divergence of mu H equal to 0, then we say that we let mu H be equal to curl of A, using the fact that divergence of a curl is always equal to 0. We use this fact. And then because of that, then the third equation, or the last equation in Maxwell, is automatically satisfied when I assume that B equals mu H equals the curl of A, it is automatically satisfied. Then what we need to do then is to make the magnetic field satisfy Ampere's law as well. So when you plug that in, what you do then is that this essentially implies that, well, I can actually multiply this equation by mu, which is curl of mu H, assuming that mu is a constant. Okay, mu is a constant. It's independent of space. And if that is the case, then if I let mu H be equal to that, then I will have curl of A. There should be a mu here, I'm sorry, because I multiply this equation by mu. Curl of mu A is mu J. Okay, I have this equation here. And then I use the famous back of the cap formula, just always bearing in mind that when I have a double curl, the parenthesis over the first curl is implied. So using the back of the cap formula, this becomes gradient of the divergence of A minus the divergence of the gradient of A is equal to mu J. And this equation looks rather complicated, but we can simplify it by assuming that divergence of A equal to 0, which is Coulomb's gauge. Okay, which is Coulomb's gauge. Then what we have then is that this term will disappear, and then we have this Laplacian of A equals to minus mu J. So we have, this is the vector Poisson's equation, and then we have this, which is the scalar Poisson's equation. So we have those two important equations to solve for static fields. Okay, but statics is good. It's simple, but it's not that interesting for applications. To make electromagnetic theory interesting, we actually have to study electrodynamics and make the solution time varying. Okay, we want to make the solution time varying. So let me move this up here. So we study electrodynamics using scalar and vector potential approach as well. Okay, now let's see how we can do that. So if you look at Maxwell's equations, if omega is not equal to 0, we actually have Faraday's law being this. I'm writing this in the frequency domain, so that's easier to solve. Okay, and then the Ampere's law just becomes J plus J omega epsilon E. Okay, and then of course we have Gauss's law for magnetic field, and then we have Gauss's law for electric flux. Okay, and we have to solve all these four equations in their full glory. And you can say that, well, actually, you just need to solve the first two because the third and the fourth are derivable from the first two. But in order to be safe, you want to solve these equations for all values of omega. Okay, we want to solve it for all values of omega. This is the mathematical symbol for all values of omega. We want to find solutions that are valid even when omega tends to 0. That is valid when omega tends to 0. So we look at all four equations and try to solve them simultaneously. So we look at the first equation. We say that, well, if we look at the first equation, it says that, well, we actually borrow something that we have learned in the past. We look at the third equation and find an immediate way to find something that would satisfy that. Okay, so one way is to let mu h is curl of A, and divergence of curl of A equal to 0. So the third equation is automatically satisfied. If that is the case, then we can actually now put mu h into the first equation, which is Faraday's law. Then Faraday's law becomes curl of E is equal to minus j omega mu h becomes A. Okay, the Faraday's law becomes that, and then we can say that, well, we can actually say that, let me see what I should say next. Sorry, I'm missing a curl here. Okay, that's why I don't know what to say next. Because when I substitute that in there, I get a curl of h on the right-hand side. And now I can rewrite this equation so that it's the same as curl of E plus j omega A is equal to 0. Okay, I put the vector potential A to the left-hand side and lump it together with the curl of E on the left-hand side. I have this equation, and this equation is reminiscent of the previous equation that we solved. For electrostatic, we have this equation to solve. For electrodynamics, we have this equation to solve. Okay, and for electrostatics, we actually solve that equation very easily by letting E equals to minus the gradient of phi. But now, since we have these two terms under the curl, so we set this to be minus the gradient of phi. Okay, we set that to be minus the gradient of phi. Then it implies that electric field is not the simple case like the static case, is just minus the gradient of phi. Okay, but for electrodynamic case, it says that the electric field is minus the gradient of phi minus j omega A. Okay, so it has an additional term that was not there for electrostatic, which is this term. When omega tends to 0, that term disappears. But when omega is not equal to 0, that term is there. Okay, and you will realize that this term actually comes from the magnetic field. It is there because we now put in the magnetic field on the right-hand side of Faraday's law. And because this term is coming from the magnetic field and is there now, we call it the induction. Like anything that has to do with magnetic field is called an inductive term, like an inductor and so on. So this is the effect of the electric field coming from the magnetic field, because electric field and magnetic field are coupled in Maxwell's equation. So we call this the induction term. Okay, the induction term. And then having done this, then we need to find equations to solve. So the third equation is solved, and we have a way of solving the first equation, but we still haven't solved the second equation yet. So let's see how we can solve the second equation, and let's plug in whatever we have into the second equation and see what happens. So in order to make the equation, the second one, solvable, I'm going to multiply it by mu. Okay, if I multiply it by mu, then I have curl of mu h, assuming that mu is a constant, so it can be taken in and out of the integral or differentiation. Then I will have mu j plus j omega mu epsilon e. E is given by this now, minus the gradient of phi minus j omega A. So Ampere's law becomes something that is looking like this, okay? And the left-hand side, I have mu h, which has been set to be this value over here. So I can actually write the left-hand side as curl of A is equal to mu j. And then I can expand this out in greater detail. So it will be j omega mu epsilon gradient of phi. And then the last term will be minus, or should be plus, because minus j and plus j give me a plus omega square mu epsilon A. Okay, I will have that on the right-hand side. Again, I'm going to use the back of the cap formula to simplify a double curl, and that becomes divergence of the gradient, or gradient of the divergence of A minus the Laplacian of A equal to the right-hand side, mu j minus j omega epsilon gradient of phi plus omega square mu epsilon A. This equation looks quite ugly at this time. It looks quite ugly, okay? Let's think of a way of simplifying it. And let's do that on the next slide, okay? So we have been attempting to solve Ampere's law. we haven't solved the last equation yet. Let's look at the last equation and see. This last equation is Gauss' law for electric field, but it is also related to Coulomb's law. So let's plug in the definition for electric field into the last equation. So we would have divergence epsilon E, but E is now gradient of phi minus j omega A. Okay, I take my E from here, plug into the last equation, and I have this being equal to rho. And let's assume that epsilon is a constant again, so that we can take epsilon outside and then take it to the right-hand side if we want to. So this is actually the same. The divergence of the gradient gives me the Laplacian, okay? And then the other side would be like divergence, let me see. If I multiply this out with j omega divergence of A, okay, is equal to rho over epsilon, because I've taken out the epsilon and assuming that to be a constant, it can be taken to the right-hand side. This equation still looks rather awful. Okay, so things are becoming haphazard in a sense, very unmanageable. Let me not put this parenthesis here. This parenthesis is not needed. But there's something clever we can do. Okay, if you look at the last equation from the previous slide, the last equation says that we have gradient of the divergence of A on the left-hand side minus the Laplacian of A on the left-hand side is equal to mu j on the right-hand side minus j omega epsilon gradient of phi plus omega square mu epsilon A. So these two equations look very ugly, and they are what are left for us to solve if we want to solve all four Maxwell's equations concurrently. Okay, but there is something clever we can do. We can look at this term, okay, and this term. There are some similarities about them. And the second thing is that we have stipulated that B is equal to curl of A. It turns out that if you just stipulate the curl of A to be something, A is not unique. And we have shown that before because you can find an A prime equal to, say, A minus the gradient of psi, a scalar potential such as this one over here. And you can plug in that. You can easily show that if this is, let me see, I use a plus sign in my lecture notes, so I better put a plus sign here. So if you were to take the curl of A prime, it is equal to the curl of A, because the curl of the last term is 0. Okay, so both A and A prime produce the same B. Okay, both A and A prime produce the same B, making A not unique. So the remedy for this, the way to get out of this problem, is to stipulate the divergence of A as well. So we have the freedom of stipulating what the divergence of A should be. Okay, and we use this freedom and exploit that freedom to simplify the third equation on this slide. Okay, if we stipulate the divergence of A to be something that exactly cancels this term, because notice that this term has a gradient. This term also has a gradient. And if I stipulate the divergence of A to be something so that these two terms cancel, then this equation becomes greatly simplified. And with this trick in mind, I stipulate divergence of A to be minus j omega mu epsilon phi. Okay, if you can see that, if I were to substitute this in here, okay, I must have made a mistake because there is a mu that is missing here. And let me track where that mu and why it is missing. Okay, so when I go from here to here, I miss the mu. Okay, I miss the mu on transferring this equation to the next line. So this should have a mu. Okay, sorry about that. And so if I do that correctly now, then this should be an equation with a mu. So if I stipulate divergence of A to be this quantity over here, then this term and this term cancel each other because they're equal to each other. Can you see that? Okay, they become equal to each other. They cancel each other, and the equation is greatly simplified. And if I rewrite this last equation that we had above, it can be written as Laplacian of A plus omega square mu epsilon of A. Okay, I just put these two terms together and put the other one to the right-hand side is minus mu of J. Okay, can you see that? So this is equal to minus mu J, and this equation is greatly simplified compared to this original one. And what about this other equation? This equation for the scalar potential phi. If I substitute this in there, divergence of A to be that, it also becomes simplified in a sense. Okay, if you do this, if you substitute this in here, minus J times minus J give you minus 1. So you actually have something that looks like, this term will just become J omega times this complicated things out here. So the equation for the scalar potential would just become that. And then the second term, if you do the proper substitution, also becomes omega square mu epsilon phi, okay, with a plus sign here. And then the right-hand side, I would just put rho over epsilon. Okay, so we have these two equations, one for the vector potential A and one for the scalar potential phi. And they look a lot simpler, and they also might have rung a bell in your mind. What are these equations that you have seen before? Or have you seen these equations somewhere in your previous lectures or lecture notes? Okay, what are these equations? Something that looks like this on the left-hand side. Remember?
Equation.
What?
The Helmholtz equation.
Very good. These are the Helmholtz equation. Okay, Helmholtz equation. Or who was that who said that?
John Liu.
Oh, Zhen Liu. Okay, Helmholtz equation. Okay, and I should say equation since there are two of them. But with the source term on the right-hand side, and in mathematics parlance, when you have a source term on the right-hand side, it's called the inhomogeneous Helmholtz equations. When you have no source on the right-hand side, it's usually called a homogeneous Helmholtz equation. It's just the terms that mathematicians used, okay? So we have seen something like this before. So then how do we solve them? Okay, how do we solve them? Well, we discuss how to solve these equations next. Okay, I should put this on the new slide of more on scalar and vector potential. How do you find A and phi? How do you find A and phi, which are my vector potential and my scalar potential? How should I find them? Well, if you look at this equation, when omega is 0, this term drops. This term drops out. And then this is just 3 equations, and we call this the vector Poisson's equation. And we use the Green's functions method to solve these equations. And when the omega is 0, this just becomes Poisson's equation. And we also use the Green's functions technique to solve this equation. And so in actual fact, we have 4 equations here, 4 scalar equations, 3 scalar equations coming from the first term, and then 1 scalar equations coming from the second equation. So in actual fact, we are actually solving a series of scalar equations, each of which looks something like this, okay? So if I just look at the x, y, z component of the first equation, each component will look something like this. If I just extract the x, y, z, I can be x, I can be y, or I can be z, okay? So it becomes a scalar Helmholtz equation. And we know how to solve this equation, and we have discussed how to solve them before. Maybe not in the lecture, but in your take-home exam. Okay, we have a similar issue with solving Poisson's equation. So if omega goes to 0, then let me see who's this. Okay, if omega goes to 0, then I would just have this being the case. Then we know how to solve this equation using something called the Green's functions method. Green's function method. Okay, in the Green's function method, we find the point source response of this equation, and then when we have a distributed source, we use convolution to find the distributed source. By the same token, if I use the Green's functions method, if I can solve this equation, okay, where I have a point source on the right-hand side, this just means a point source, okay, point source. Beta is my usual wave number, omega squared mu epsilon, okay. And if I know how to solve this equation, then I know how to solve the above equation using the principle of linear superposition. And we have solved this equation before, okay. When beta equal to 0, we convince ourselves that this Green's function is equal to 1 over 4 pi r minus r prime, okay? And in your take-home exam, you have convinced yourself that when beta is not equal to 0, you can find this to be e to the minus j beta r minus r prime over 4 pi r minus r prime. Okay, in your take-home exam 1, you convince yourself of that, and you can either verify this by back substitution and show that it's satisfied this equation, very importantly, or you can also start from first principles. Okay, you start from first principles and you go through the math carefully. You find that, in fact, the Green's function of this equation is that. And once you know how to solve this equation with a point source on the right-hand side, okay, you can use the principle of linear superposition to find the case when you have a distributed source on the right-hand side. And you can do the same to the other equation, okay, which is this equation over here. You find the point source response of this equation. And then once you have found that, you can use convolution or the principle of linear superposition to find the solution when you have a distributed source. So I'm going to just write down the solution for you without deriving it, because you know how we get there, okay? So the vector potential then would be just the convolution of the Green's function, okay, with the volume integral. And I can write the convolution of the Green's function with the current in this manner. Okay, and then the scalar potential then would also be equal to the convolution of the Green's function, because for the scalar potential part, I will have 1 over epsilon on the right-hand side times rho, whereas for the vector potential part, I have mu times j. So it will be a very similar convolution, okay? Instead, you put a source here. Voila, we have found the solution to these two complicated equations. The vector potential, and one is for the scalar potential. And this is what? The scalar potential. So are there any questions for this? Any questions for this derivation? Is everything is fine and dainty for you? If everything is fine and dainty, then we can move on. We can move on to do something more interesting. So I'm going to talk a little bit more about vector and scalar potential case. When you have, let me see, let me insert a new slide. Okay, when you have magnetic sources, and we have fictitious sources like magnetic sources. Okay, J becomes M, and then magnetic charges. So Maxwell's equations just becomes curl of E equals to minus J omega mu H minus M. And then curl of H equals J omega epsilon E, E plus J. Okay, and then you have divergence of mu H, not equal to 0 now, but equal to the magnetic charges, divergence of epsilon E equal to electric charges. Okay, and of course you have the continuity equation, the divergence of J must be equal to J omega rho sub E. Okay, there should be a minus sign here, divergence of M equal to minus J omega rho sub M. Okay, these are charge conservation equations. Okay, they imply charge conservation, and they also call the current continuity equation. So how do we solve Maxwell's equations now with M and J present? We can do that by using the principle of linear superposition that you have done in your course, because we are dealing with the linear system here. Okay, we have a linear time invariant system, LTI system. Our inputs are M, J, and then rho M and rho E. And their outputs are E and H. Okay, so you can think of this as a linear time invariant system. You can actually first, for instance, set M equal to 0. You only have J, and then you only have rows of E, and then you will have the output as E coming from the electric sources, H coming from the electric sources. And then you can also now, because this is a linear system, now you can put M to be non-zero, but J equal to 0, and then put rows of M. And then these are the fields coming from magnetic sources. Okay. Now, if you were to deal with a linear system, and if you know the solution to the second problem and the third problem, if you know how to solve the second case and the third case, you will use the principle of linear superposition to find the solution to the first case using the property of a linear time invariant system. Okay, and I'm sure that as an electrical engineer, you have studied this before. Okay, and you can convince yourself, because everything in this equation is linear. You can put this as the input, and this would be your output. Okay, you can convince yourself that you can set this one of the sources to 0, you solve these equations, and then next time around you set the other set of sources to 0 and solve these equations. And when you add these two solutions together, you will get the output when all the four sources are present. Okay, I'm not going to go through the exercise to convince you of that. But what it says is that once you know how to solve the case where J is not equal to 0, M is equal to 0, and rho sub E is not equal to 0, but rho sub M equal to 0, you can also find a solution to the second case by invoking duality principle. Okay, you can invoke duality principle to find the second case, the solution for the second case. And then it would be quite straightforward then to write down the total solution when all the sources are not 0. They are all turned on. Okay. Are there any questions on this, the use of principle of linear superposition to find the total solution when all the sources are not turned off? All of them are turned off, are turned on, I mean. Okay. If there are no questions, then I'll move on to talk about something different from this. Okay, I think I have the slide here, which is the question of when is static electromagnetic theory valid? When is quasi-static electromagnetic theory valid? Because we started out with static electromagnetic theory. We deal with scalar potential and vector potential. And then we end up with studying vector case, where we end up with a more complicated set of equations to solve. Okay, so in other words, we have the vector potential being equal to this now, and then we have the scalar potential being equal to this now, whereas previously we just had this. And then we just had this. Okay, this is simpler. So the question we ask ourselves is that when can we confine ourselves to just solving Laplace's equation and not having to solve Helmholtz? This is Laplace. This is Helmholtz. This is Laplace. Or maybe I can say Poisson. Okay, they're both French. Okay, so when can you replace the left-hand side with the right-hand side? What is the rule of thumb? Well, if you're a fluid person, you will do what is called a dimensional analysis. And what you do then is to compare the size of these two terms. When is this term small compared to this term? Okay, so I'm going to do the dimensional analysis rather quickly. And the Laplacian is partial square, partial x square, plus partial square, partial y square, plus partial square, partial z square, and it's having a dimension of 1 over L squared. Okay, and beta square is 2 pi over lambda square. It also has a dimension of 1 over length squared. But beta is a constant. But Laplacian square depends very much on the geometry. Laplacian square is a measure of how rapidly the field is varying. If the field is varying rapidly, then the Laplacian of that field will become large because you're taking derivative of the field. The more rapidly the field is varying, the bigger it becomes. So the question next to ask is that when would the field be rapidly varying? Well, I did a number of dimensional analysis in the lecture notes, but I'm going to cut through the chase and use a short argument here. And I want you to eyeball this picture. This picture is the picture of an electric field and magnetic field in the vicinity of an object. And you can see that in this picture, the electric field has to contort itself to satisfy the boundary condition on the surface of the sphere. And then the magnetic field has to contort itself to satisfy the boundary condition on the surface of the sphere. And you know what those boundary conditions are, okay? And if you go back and revisit your boundary conditions, the boundary conditions are n cross E equal to 0, and the other one for magnetic field is n dot B equal to 0, okay? And you can also say that n cross H equal to J, okay? There will be surface current on the sphere surface, and n cross H has to be equal to that in order to satisfy these boundary conditions. Okay, the field have to be what I call a contortionist. You know what a contortionist in a circus is, okay? They have to contort themselves to satisfy the boundary condition. And you can imagine that the smaller the sphere is, okay, the more rapidly the field have to contort themselves. Okay, so roughly speaking, you can say that partial x is proportional to 1 over L. That is, the smaller the L is, the larger is going to be partial x. Okay, and the same for partial y, and then the same for partial z. All this have to be varying on the length scale of 1 over L. The smaller the L is, the larger the rapid variation of the field, and then the larger will be these derivatives. And what I'm trying to get it here to cut through the chase is that this Laplacian would be proportional to 1 over L squared. Okay, and I should not put this 1 over L squared on the second term. Okay, it has the dimension of 1 over length, but I need not have to put them there. But now if you compare the two terms, okay, if you compare the two terms, Laplacian's square would be proportional to 1 over L squared. And then the ratio between the two terms is that if I were to write this equation, I'll be comparing 1 over L squared with beta squared, which is 2 pi over lambda squared. Okay, if you compare these two terms, then you can see that when when the wavelength is very, very long, okay, if the wavelength is very, very long, then it says that beta L squared would be much, much less than 1. Okay, if you write beta L squared would be 2 pi squared L over lambda squared. That is, so if we compare the size of the two terms, this term will be much smaller than this term if this is true. Or when the length of the object that you're inspecting is very much shorter than the wavelength, then you can drop this term. You can drop this term compared to this term because this term is large, and you can replace Helmholtz equations with Laplace's equation. Okay, so you can do a static approximation of electrodynamic theory when that is the case. And that is the case when you are, for instance, dealing with nanoparticles. Even in optics, the frequencies are very high. Omega is on the order of 10 to the 16 maybe in optics. Okay, but the wavelength is about 400 nanometers. But the size of the particle is on the order of 10 nanometers, for instance. So we satisfy the requirement that beta square L square is much, much less than 1. And you can actually analyze nanoparticles using electrostatic theory or magnetostatic theory. And hence, if you have a light wave impinging on the nanoparticle, and if this nanoparticle is very small compared to wavelength, you can go back to the beginning of your course and analyze this problem using electrostatics. And that you have already done in your homework. You find that the electric field outside is given by this, okay? Inside is given by this thing, okay? You did that in your homework. And you found what ES and EI is. This is a scattered field, the dipole moment. From here, ES is this one. You have already found that in your homework. You have found your EI, and they're given to be this solutions to statics. And this is very interesting, even though the wavelength is very long compared to the particles, but the frequency is not low, okay? And in the case of plasma, if these are plasmonic nanoparticles, you remember that epsilon for plasma is 1 minus omega p square omega square, okay? And this can be negative if your frequency is less than the plasma frequency. And when the particle has a negative permittivity, these two terms can cancel each other. And when these two terms can cancel each other, you get infinity values. And you remember what infinity values mean. Can anybody tell me what happens when you encounter infinities? We have encountered infinities on several occasions. Anybody wants to give a try to my question as to when
You'll
this
get
thing becomes
resonance.
infinite, what does it mean?
You'll get resonance.
Yes, we get resonance. We found that in the Fresnel reflection coefficient for studying the surface plasmonic mode. We found that in finding the guided mode of the dielectric slab. We found that at several occasions. You found that in the LC tank circuit, for instance. It means that you encounter a plasmonic resonance, okay? So you can get this plasmonic nanoparticles to resonate, and they will have a very strong glow when you shine light on them. However, you can change the resonance frequency of the glow by changing the background material. That's what they do here. Okay, they put the nanoparticles in fluid with different permittivity, and you get different colors coming out of them. Okay, and I don't have time to get into here, which is the fact that when you are in the static regime, you can deal with circuit theory. Circuit theory has components that are called capacitors and inductors. And those are very important in circuit theory. They emphasize the fact that the displacement current in Ampere's law cannot be thrown out. The flux linkage in Faraday's law cannot be thrown out. And if you can do all this engineering to amplify those flux linkage as well as the displacement current, you can have all the terms in Maxwell's equations to be there in circuit theory as well, okay? So the next time we will study circuit theory and how it comes from Maxwell's equations as to why circuit theory can replicate many of the phenomena that we have observed in Maxwell's equations, because we do engineering to keep the induction term or the flux linkage as well as the displacement current term as much as possible. Okay, I'll stop here. I'm running over time. Are there any questions before we depart? If not, then I'll let you go then, and thanks for coming, and you keep safe out there. Okay, you keep safe out there.
Thank you,
Thank you.
Professor.
Take good care of yourself.
Thank you.
Okay, stop sharing now.